member states and respected audience. Good afternoon, and I welcome you all on behalf of SARC Energy Center. Thank you for joining us today for the webinar on buildings to grid integration. I hope that you all are safe and doing well, and I wish you all excellent health. The audience, the concept of building to grid integration entails the exchange of energy data information between the buildings in the grid. This exchange enables the buildings to act as distributed energy assets for the grid, thereby resulting in a more efficient, green, and reliable energy system. Considering the ever-growing demand of electricity in the cities, the evolution of distributed generation, the advent of smart metering, control, and sensing technology, the integration of the buildings and the power grid will all become inevitable in the smart cities of the future. Given the potential benefits of grid interactive buildings, SARC Energy Center decided to conduct a knowledge-sharing webinar under its thematic area of program to successfully implement technology transfer. We have brought together a panel of expert speakers from USA and Spain to share their insights on different aspects of the topic, such as the importance of building to grid integration, enabling technology, and the ongoing research. I certainly hope that it will be an intriguing session and will disseminate useful information to our audience. Before proceeding with the agenda, I would like to draw your attention towards certain things related to the webinar. Please note that the agenda of this webinar is already available on SEC website, and you can also access it through the GoToWebinar panel on your screen in the handouts section. All the presentations, a brief report on the webinar, and the recording link will also be uploaded on SEC website.
Or as we've dubbed it, Grid Interactive Efficient Buildings, or GEB for short. I want to ground my comments in the dramatic changes that are taking place in our electricity system. With the expansion of new technologies, including variable renewables, distributed generation, energy storage, and electric vehicles, buildings will need to play a critical role in enabling the transition to a clean, reliable, resilient, low-cost electricity system. In the U.S., buildings currently play a major role in the electricity system and are responsible for about 75% of total electricity consumption, and in many regions are the primary driver of peak electricity demand. However, buildings all too often are viewed by grid operators as a load that needs to be served, rather than a resource that can be called on to meet grid requirements. We believe that as the primary consumer of electricity, turning buildings into a reliable resource for demand flexibility, we can unlock a wide variety of economic and environmental benefits that would benefit both building owners and occupants, as well as grid operators and society writ large. At the Building Technologies Office, we start by thinking about how changes in energy use in buildings will affect consumers. Here, we have a person who is doing some work near a window. Now, if this window is inefficient, perhaps it's only a single pane of glass, and maybe there's no low E coating to prevent solar heat gain, this person is likely going to start feeling hot, and perhaps their computer screen is going to become uncomfortable to look at because of glare. Now, in a grid interactive building, sensors would detect these issues and would engage responses from the building's equipment to fix these problems. Perhaps the shades would be adjusted. Perhaps the air conditioning system would redirect more cold air to where this person is until the temperature is brought into reasonable comfort bounds. But we believe that by communicating with the grid, buildings can also provide additional value. Buildings can provide this value by being efficient, reducing the total amount of energy needed to deliver the energy services that building occupants want and need. But this value has been known for decades. The new innovation is the buildings to grid component. That is, communication between connected devices that can change their energy use patterns in response to grid and occupant needs in an intelligent way. Allow me to break this down a little bit more, as it's important for GEBs to have all four elements included in this graph. First, it's energy efficiency, which, as I said, is minimizing the amount of energy necessary to provide any particular energy service. Second is connectivity. Buildings or building equipment need to be able to both send and receive signals from the grid or grid operator. Third, flexibility. This is about responding to this communication in a way that provides this requested grid service. And finally, intelligence. These responses need to be effectuated without damaging the equipment or inconveniencing building occupants. So there's an element of reducing the amount of total energy used. There's a communication between the building and the grid. There's a response that provides the necessary grid service, and this all needs to be done in a way that provides the maximum benefit to both the building occupant, building owner, and the utility or grid operator. So what do these changes look like? At BTO, we broadly talk about 4 types of changes to building energy use. First, there's energy efficiency. From this perspective, it's a persistent reduction in the amount of energy needed to provide a given service. For example, installing a more efficient heat pump water heater in place of a traditional electric resistance water heater. The total amount of energy this new efficient device uses would be less than that of the previously installed equipment. So persistent reduction, a reduction that lasts over days, weeks, months, years, potentially decades. Second is load shedding. This is basically traditional demand response, where we temporarily reduce the amount of electricity a device is using. This can be engaged in a variety of ways. For example, I might sign up for a utility program where I receive an SMS message on days when the grid is stressed with a request to turn off my air conditioner for an hour or two. If I take this action, I'm helping to shed load. However, this isn't grid interactive in the way we conceptualize it, because I'm taking the action directly as opposed to the grid communicating with my water heater directly. We prefer if the air conditioner automatically turned off its in response to a signal from the utility. This can be better both from the building occupant and for the utility. As I said, I wouldn't have to change my thermostat set point in response to an SMS, and the utility would be more confident that it could get the necessary load reductions from a program that's enacted automatically as opposed to through SMS messages. As this has been amply demonstrated by Richard Thaler and Cass Sunstein and others, that reducing even small barriers can drastically increase participation rates in programs. Third is load shifting. This is about changing when a piece of equipment uses energy. To return to our water heater example, we could preheat the water, perhaps coincident with peak solar production, and then later in the day, we turn off the resistive element in our water heater and just use the stored hot water. Or for our air conditioner example, perhaps before sending a signal that turns the system off, the utility could also send a command to pre-cool. That is, to temporarily reduce the set point of the system to make sure that the building's thermal mass is cool enough that we can coast through several hours of the air conditioner being off. Unlike efficiency and load shedding, the total amount of energy used by equipment when shifting load could be more, less, or the same amount as the energy used under typical operating conditions. Finally, there's modulation. These are sub-second changes that can be layered on top of a piece of equipment's usual energy consumption pattern. These sub-second changes in energy use can provide different grid services, such as frequency regulation or voltage support, to help maintain grid stability and power quality. Providing these services on a regular basis is what we mean by demand flexibility. Demand flexibility in buildings will deliver a variety of different benefits. One of the central motivators is reducing the cost of energy. U.S. businesses and households spend over $400 billion a year on utility bills. By enabling buildings to shift when they consume energy, we will be able to defer costly system upgrades by increasing the utilization of transmission and distribution system resources, and we can reduce the amount of time that expensive peaker plants are used. And given the market structures in the U.S., these changes will result in lower energy bills. Another major benefit is the potential for reducing greenhouse gas emissions. Buildings will be able to align their use with intermittent resources such as solar and wind, so we can take advantage of these low-cost, carbon-free energy sources. Obviously, these economic and societal benefits are important from a policy perspective, but we believe that if the technologies are properly designed, consumers will also experience real quality of life benefits that will enable the rapid transformation of the energy system. So I presented about the concept of grid interactive efficient buildings. Now I'll introduce you to the work that BTO is doing to make this concept a reality. BTO organizes its GEB portfolio into 4 broad categories of work: analysis, technology development, real-world validation, and system optimization. I'll go through examples of each of these in turn to give you a sense of the type of work we're doing. As an analyst, I love to start with analysis. I'll talk briefly about 2 projects, the first of which is Scout. Scout is a tool that allows us to compare building energy technologies on a fair playing field so we can identify areas with the greatest opportunity to reduce energy use at the lowest cost to the government and consumers. In the past, Scout only considered the annual energy savings of different technologies. So to enable us to consider the flexibility I previously mentioned, we are augmenting Scout by enabling it to consider energy use on an hourly basis. To do this, we need to leverage physics-based digital simulations, which are run using OpenStudio and Energy Plus. Doing this allows us to consider how new technologies will behave in various building types across all regions in the United States without having to do extensive laboratory testing. The other effort I'd like to mention is our analysis on the time-sensitive value of energy efficiency. This analysis is looking at the attributable costs associated with different energy end-use profiles in buildings. On the top graph, you see the estimated value of saving 1 megawatt hour of different end uses based on data from the state of Massachusetts. And you'll notice that residential heating, ventilation, and air conditioning is twice as valuable as that of the other end uses considered. That's because Massachusetts is a summer peaking state, and so saving energy during that peak season provides more value. On the bottom graph, you'll see the ratio of time-sensitive versus time-insensitive values across different regions within the U.S. This analysis is not just about setting time of use rates, but it can also be helpful in designing other policy instruments to get the most out of the building energy efficiency. We've already published several reports on time-sensitive valuation and expect to have the Scout estimates of the potential value of GEB technologies for the U.S. building sector in the next few months. And I'd be happy to share these reports or any of the other resources I'll mention if it would be of interest to you. On to R&D. Technology development is one of BTO's core functions. BTO has an entire team working on emerging technologies. And to help guide the work that this team does, BTO has commissioned several technical reports that assess the capabilities that various technologies have for providing grid services. These reports also address the challenges that adding these capabilities might face, both from a technology perspective as well as from the perspective of that particular technology interacting with the grid. Building on this work, we are writing a series of research and development opportunity documents which are essentially technology roadmaps that highlight both the specific technological solutions that have the greatest potential for energy efficiency and demand flexibility, as well as cost and performance targets that we think can be achieved over the next 5 to 10 years. Once we have new technologies, we need to confirm that they actually perform as we expect in the real world. I picked this project because it focuses on getting grid interactive efficient technologies into existing buildings. In the US, we have over 120 million buildings, and under normal economic conditions, we add about 1 million new buildings to that stock each year. So if we're going to make real impact on building energy use, we need solutions for existing buildings. This project was jointly conducted between the New York State Energy Research and Development Authority, or NYSERDA, the National Renewable Energy Lab, and Consolidated Edison, a utility that operates in New York State. And it looked at low-touch or no-touch approaches to adding energy management systems to existing residential buildings. This pilot gave valuable feedback on what worked and what didn't, and this project will be used to help the utility roll out a successful program at scale. While I picked an example of validation in existing buildings, I want to be clear. We are also working on projects that focus on new buildings with community-scale projects in Georgia and Alabama, which were done in partnership with Southern Company, a regional utility in the southeastern United States, and Oak Ridge National Laboratory. Looking forward, the Building Technologies Office is planning on releasing a request for proposals for $40 million in community-scale validation. This request for proposals covers both new and existing buildings, and is expected to be awarded over the course of the year. With the current COVID-19 pandemic impacting both the economic activity of communities as well as their energy use patterns, it is now more important than ever these types of real-world validation projects move forward so that we can document and share their lessons learned to drive further reductions in the amount of energy and money that is wasted by inefficient technologies or unproductive operations. Finally, optimization. This element relies on the previous three to be successful. We need to get the valuation right. We need to have the technologies that can deliver the needed services to the grid, and we need to make sure they meet consumer expectations. Once we have all of that together, we need to make sure that they are implemented in a way that maximizes benefits to building owners, grid operators, and society as a whole, while also minimizing costs or unintended consequences. Part of this is understanding how energy is actually used. On the left, we have an image of the energy consumption of domestic hot water heaters. The top graph is the population use pattern over the course of a day. And at the bottom, we have the same use over the same time frame, but for a single home. This increased variability in a single home's energy use patterns means we might need to rethink the characteristics of the technologies we're working on to meet the needs of different households, rather than solving for some typical population use pattern. This becomes even more apparent when we consider distributed variable renewable energy generation and that interaction with building energy use. In the middle panel is on the top graph, we have a single day's electricity use for a building with on-site PV shown with hourly time steps. This top graph shows the hourly resolution of electricity use and generation. And based on this analysis, it's showing that the building will consume about 17 kilowatt hours of the energy it produces. The bottom graph shows this data for the same house on the same day, but in 1 minute time steps. And this shows that doing the analysis with hourly time steps over-predicts self-consumption by more than 30%. So what I'm saying here is the granularity of the analysis that you do impacts the conclusions that you draw from that analysis. And that's even more important with grid interactive technologies. When more buildings begin producing their own energy, this type of granular analysis becomes key in making sure that buildings are providing services to the grid rather than making demands that might stress the distribution system infrastructure. I'll end with this image, which I love because it shows just how quickly the world can change. These are two pictures of New York City. On the left is a picture that was taken on Easter Sunday in 1900. The street is packed, and there's only one car to be seen. On the right, it's Easter Sunday 13 years later, and while the streets are still packed, the situation is reversed, with only one horse-drawn carriage in the photo. While the building industry in the U.S. is known for changing slowly, I believe that grid interactive buildings have the potential to revolutionize the energy sector much more quickly than past changes have been enacted. So don't blink or you might miss it. Thank you very much, and I look forward to our discussion.
Thank you, Mr. Jack, for your excellent presentation. It was very informative and comprehensive. I think our audience must have greatly benefited from your presentation. We shall now take a few questions that we may have received. So let me just questions. So based on your experience in the US that you have shared, how many pilot projects have been done on this concept already?
We don't have a comprehensive list. The U.S. is a federal system where, obviously we have a strong central government, but states have a lot of responsibilities for enacting local policy. And one of those things is building regulations and regulations of the utility sector. So California and the state of New York have done a large number of these types of pilots. The Building Technologies Office has done dozens of these types of pilots at various levels of complexity. Obviously, building interactions with the grid go back to the time of Thomas Edison and the Pearl Street Station, when the first building was connected to the first power station. So I don't believe there's a comprehensive list that answers that question. Sorry, I'm not able to give a direct answer to
that. We have a question. What's the payback period that you think for anyone within a grid interactive building? What would be the payback period and the cost to benefit ratio? Do you have any data on that?
Sure, yeah, we do have some data, and this is primarily based off our experience with energy efficient technologies. So in the commercial sector, many building owners are looking for very short payback times. 1 to 2 years is not atypical for building owners who have large portfolios and are interested in presenting green, environmentally conscious perspective to their customers and clients. They're often willing to take longer payback periods, but still relatively short. 5 years is kind of what we found as the 90th percentile upper bound of the length of time. Obviously, there are owners who are willing to go well beyond that, but 1 to 2 years for typical building owners, and then 5 years for environmentally conscious building owners in the commercial sector. In the residential sector, it's much more diverse, and so consumers are willing to accept very long paybacks if they feel that they're getting the services and the benefits of a new technology. They may even take a negative return on investment from a capital cost perspective if they feel that it's providing some additional resilient or other benefit to them.
Okay, we have a question from India. Can you please expand on who should pay for these innovations versus who gets the benefits? It looks like the utility gets the most benefits.
Certainly, yes. That is an easy way to see how this plays out, right? That the utility is able to reduce their costs through the control of end-use devices in the building. We don't see that that is necessarily going to play out. We think that consumers are going to need some financial inducement to sign up for these programs or allow the utility to control their devices. As I mentioned with the time-sensitive valuation work, this isn't just about time of use rates, which is one tool that utilities are using to help nudge people in the direction of being more conscious about when they're using their energy to reduce total system costs. We think that these technologies will both keep upward pressure on utility rates low so that all consumers benefit from a more flexible building stock. And then two, the specific customers who are using grid interactive technologies will probably be compensated by the utility, or it could be a state or a state government that provides some tax relief for people who install these technologies in their buildings. So they might get, say, a $50 a year rebate from their utility for enrolling in a grid interactive program.
Okay,
I guess
thank
the
you.
other thing, the other thing I'll say with that is I think there is a really strong diminishing marginal return to demand flexibility once we get to really high levels of penetration. Similar to solar, as you get more and more incremental solar on the system, the marginal value of that solar decreases. So I do think there's some equilibrium point where a reasonable amount of demand flexibility provides the bulk of the value.
Okay, thank you for your answer. The next question is also from India. For plug-in demand control, is there any tariff benefit?
I'm sorry, can you repeat that, please?
For plug-in demand control, is there any tariff benefit?
I'm sorry, I'm not familiar with plug-in demand control. Is this a question about electric vehicles?
No, I think they want something from your presentation. I think someone picked up from your presentation. But for the next question, while we get some clarification on the question, the next one is there any law related to this grid efficient buildings? These buildings are now mandatory by law in US?
No, they are not mandatory by law. This is voluntary. As I mentioned, we're in a federal system, and so the U.S. national government doesn't have a strong role in setting building regulations. We do have the responsibility of regulating the efficiency of end-use equipment. So there's a minimum performance standard for refrigerators and air conditioners and water heaters and 60 so other residential products, as well as dozens of products in the commercial sector. But we don't regulate anything around the demand flexibility of those technologies. Now, the Energy Star program, which some of you may be familiar with, does have a credit system that allows manufacturers to reduce the amount of energy efficiency of an Energy Star product below their typical threshold if that device meets certain demand flexibility requirements. So it's not mandatory, but you are able to get this certification, which consumers look on very favorably for select products that have demand flexibility capabilities.
Okay, here the next question is from New Jersey. Which software would you recommend for this energy efficiency analysis for buildings?
Well, I would say it depends on what question you're asking. We have a variety of tools that we use to look at different problems, whether that's individual piece of equipment. We have models of heat pumps and lighting and daylighting systems that give us insight into how a particular piece of equipment or a subset of a building system works. We also have, as I mentioned, full building modeling tools, our Energy Plus and Open Studio platforms. We have tools that look at districts or small communities of buildings. That's our Urban Opt platform. And then we also have a variety of national scale energy modeling tools. Scout is, I would say, at the easier to use, more quickly run end of that spectrum. It's really for scenario analysis, comparing large sets of measures to see how they stack up against each other in terms of the cost-benefit ratio. But we also have more computationally intense tools, such as our ResStock and ComStock models, which attempt to simulate the entire U.S. building sector at high resolution of both equipment detail, geographic resolution, and time step. And those tools take a lot of resources to run, but they give us detailed insights. And so after we down select with Scout the measures that we're particularly interested in, we can validate those results with this more intense energy simulation tools. Obviously, there are also grid tools that need to be considered, grid models, whether that's at the distribution system level or the transmission level. And so I think among that suite of tools, the real question is, what are you looking, what problem are you looking to solve? And then we select from that basket.
Okay. The next question is also from New Jersey. What are some of the data requirements when doing an energy efficiency study?
Yeah, so let me just go back a couple of slides. I think this is a really good example of the type of data that you need. So obviously this is at the household level, but we can also look at population data. But we want to have high time resolution, and that can mean a variety of things. It doesn't need to be 1 minute time steps. It could be every 5 or 15 minutes, and even hourly data gives us a lot more insight than annual data. And for other tools that we have, we also look at seasonal data. So we might have 10 time steps that look at on peak, off peak, typical operation days, and then perhaps one for our system max peak day. And oftentimes that level of resolution gives us sufficient insights to cut some technology options and focus on a smaller subset with this higher granularity resolution. But we need to have time resolved data. It's really important to have that linked with a particular location so that we can sync up the weather file. So we need to know what's going on in the outdoor environment because at least in the US, our loads are driven by the HVAC systems. Most of the US is summer peaking, but we do have systems that are winter peaking. And obviously the solutions for that, those regions are very different than for the rest of the United States. So high time resolution, synced with a geographic location. And then we also need to have grid data. We need to know how does the building's energy use pattern relate to the energy use of the power system that it's on. In the U.S., we have essentially three grids, and what's going on in Texas is very different than what's going on in the Eastern Connect, and that's very different than what's going on the Western Connect. And obviously, the grid breaks down into smaller components at the regional level, and then again at the local level. And depending on which problem we're solving for, we'll want different geographic resolution as well. So hopefully that answers the question.
Thank you. The next question is, I think, related to the existing buildings and their conversion to grid interactive buildings. So the question is, are there any financing facilities available or incentives available for conversion to grid interactive buildings? So like somebody, please go on.
Yeah, so for Consolidated Edison, or Con Ed as it's shown on this graph, yes, they are rolling out a program across their utility territory for existing building upgrades that incorporate these home energy management systems that will further facilitate grid flexibility. There are some programs in California that are based on market mechanisms, so those aren't utility driven, but rather they're third-party energy aggregators. So this would be a company that goes out to commercial building owners or households and says, if you sign up for this program, I will pay you based on the performance of your devices. And occasionally they will offer financial incentives financing capabilities for to help people sign up, or they will gamify, quote unquote, their participation, allowing the typically homeowners to gain points and then spend those points for additional technologies, whether that's a smart power strip or a smart plug or a Nest thermostat. Those are the various types of programs. So there are a small number of utilities that are managing their own programs, and then in the state of California, there's this open market for demand flexibility, which is unique to the U.S. right now.
So we got the explanation on the question that I asked you before. The question is now, when customer accept for demand control by allowing in plug-in control for demand reduction, whether customer tariff is reduced?
Typically, it's not. People may sign up for this demand control along with time of use rates, in which case they may be able to more effectively shift from high rate periods to low rate periods. But typically, they're not getting any special rate. I might sign up for a time of use rate and not have any demand flexibility technologies in my house. But that I would be paying the same time of use rates, the same tariffs as somebody who is in that program with demand flexible technologies. They'd just be more able to change their energy use patterns to minimize their total bill, whereas I may need to engage in, more human-driven activities to reach that same, minimization level.
Okay, so the next question is, can you please mention the role of storage in load shifting?
Sure. obviously, battery storage is a huge component of this, and battery paired with solar is a very popular approach for maximizing on-site solar generation and minimizing energy bills. But at the Building Technologies Office, we don't work on battery storage technologies, but we do work on thermal storage. And so that includes things like phase change materials, and looking at energy storage in water heaters or ice storage in HVAC systems to help shift energy use without incurring the additional cost of a standalone battery storage device. And there are some benefits to each of those technologies, but they're limited to thermal applications. Whereas with a battery, you could use that to watch TV during peak periods or keep your lights on, non-thermal applications. Another thing that often is associated with this is fuel switching. So in some locations, particularly remote communities, people look at dual fuel systems, so natural gas or electricity, or less likely or less common is fuel oil and electricity. And so that allows a building owner or utility to shift between those two fuels depending on what the needs of the electricity system are, without impacting the building owner at all. It's a different type of flexibility.
Okay, another question is, this is actually a professional working with World Bank in India. She's asking, in SAARC countries, the utilities are all short of revenue and have difficulty covering their costs. How do you think they should embrace the idea of energy efficiency, meaning that they will sell less kilowatt hours and get less revenue? This is the biggest difficulty we have in dialogue with utilities.
Yeah, this is, I think, really a market structure question. In the U.S., we have a couple of different ways that our markets are structured. Again, this is done at the state level. So some states have traditional regulated utilities, which typically face a cost plus recovery model. So their utility rates are set such that their capital costs are fully covered and the operating costs are fully covered, and then they're guaranteed a rate of return on top of that. And that rate of return is typically based off of capital investment. So selling additional kilowatt hours doesn't get them more revenue, but building a new power plant would. So that's kind of how we handle it in the U.S. Other markets are competitive markets where utilities bid in an organized market for contracts to provide power every 15 minutes of the day, a day ahead, and sometimes years out for capacity markets. And so that's a very different market structure, and the distribution and transmission resources are owned by a different entity that manages the grid. That's why occasionally I would talk about grid operators rather than utilities, because in some regions those are separate entities, and in other regions those are the same entity. So I don't really have a solution to propose, but only to say that I think this is really a regulatory issue rather than a technology issue. Obviously, adding flexible technologies is going to change the calculus of utilities, or could change the calculus of utilities in terms of what they decide to focus on. The real issue is making sure that it's not negatively impacting utilities to have these technologies going out, because then you're going to have a important part of the economy and the interest groups associated with that really not supportive of the proliferation of these technologies, which we think have real important environmental benefits.
Perfect. So I'll just take the last question that we have. It is from Pakistan. So the question is, it seems like the consumers have to align their preferences according to the control signals, restricting them to follow some kind of instructions, robotizing the lives to support the grid. So in what way the flexibility of the end user is respected? I mean, this could potentially reduce the number of consumers to participate in such programs. So what's your take on this?
Yeah, that's a great question, and that's what I was hoping to emphasize in this one of the early slides that I showed, where we have the person working here at their computer. Obviously, there are different technologies that respond in different ways to demand flexibility requirements. An HVAC system or a water heater, those are really prime for demand flexibility because we can shift their energy use patterns by small amounts, and consumers are going to see no loss in welfare, no loss in the energy services that they're ultimately getting. Whereas a computer, or worse yet, in America, a TV, if you were to shift when that device was drawing energy, people would be very upset. I don't know how it is in India or Pakistan, but I imagine that if TVs went off during an important cricket match, people would be quite upset. And so we need to be cognizant of the end-use technologies that we're impacting. I think lighting is somewhere in a middle zone because we can, with proper building design, have daylighting where windows are placed in strategic locations, where we have reflective surfaces, or how we design interior spaces means we might be able to adjust lighting levels some amount without really affecting people's experience in the building. But it's constrained, whereas things like a water heater or a refrigerator or HVAC system, we have a little bit more playroom with the thermal mass of the building or the device to take advantage of. And then I guess thirdly is white goods. So things like dishwashers, washing machines, clothes washers. Those are devices that if consumers change their behaviors in some small ways, we might be able to take advantage of that demand flexibility. But consumers need to change their expectations that when I hit clean on my clothes dryer, it may not immediately start. It may wait 30 minutes because that's better either from an economic perspective if I'm on time of use rates, or if I'm participating in some control program, that may be waiting because of the conditions on the grid.
Yeah. Okay. Thank you, Mr. Jack, again for your time for and doing this webinar this early in the morning. And it's also interesting to note that as an American, you know about cricket as well. I don't think many Americans know about it. So yeah, good for you.
Well, thank you. It was wonderful talking with you this morning. And as I said, if there are any reports or additional resources that any of the participants would like to follow up on, I'm more than happy to either connect you with the relevant experts here in the U.S. or provide you the resources that I mentioned. I hope we have the opportunity to speak again in the future.
Absolutely, would love to collaborate with you in future as well. So if anybody asks for some relevant data or the connections, I'll definitely let you know. Thank you for joining us again, and take care and stay safe, stay home. Thank you.
Thank you. I will. Goodbye.
Goodbye. Bye. So, dear audience, we'll now move to the second session of our webinar. We'll be joined by Professor Dr. Pablo Arboleda from University of Oviedo, Spain. The topic of his presentation is the electrical distribution ready for a revolution? Where he will be talking about the evolution of electrical distribution network for the future. Professor Pablo is currently working as Associate Professor at the University of Oviedo. He is the co-founder of the LIMO research group, in which he carries out his research activities related to the modeling and analysis of electrical systems and the implementation of operation and energy management techniques. Mr. Pablo is holding the Smart Cities chair at the University of Oviedo, funded by the city of Gijón. Aligned with the target of this chair, he participated in the development of Gijón Demo Lab, in which an IoT infrastructure at city level is being tested and developed. He is also the co-founder of FlexiGrid, University of Oviedo spin-off technology-driven company that develops software tools specifically designed for grid operators, aggregators, and energy communities. On a personal note, he's also my former professor. So welcome you, Professor Pablo, and good morning to you. Thank you for joining us today to share your insights on the progress of electrical distribution network.
Thank you very much, Ahmad, for this presentation. It's a pleasure for me to participate in this webinar today. Today, in this presentation is quite aligned with the previous one about the integration in buildings in the electrical networks, but since the previous presentation was more related to building aspects, right now we are going to talk about a little bit about the grid integration. Is it possible to integrate these smart buildings in the grid? So the answer is totally, definitely yes, but we need to change something in the grid. No, we cannot make this integration in the grid as it is right now. So some changes must be done in the grid. But when you talk about that with people in utilities and grid operators, sometimes the feedback is why to change something that it's working and it's working fine. For instance, in Spain, the number of interruptions that we have in the distribution level is nearly zero. So things are working and are working fine. So which are the drivers for changing the distribution grid in order to be able to allocate all these distributed resources, buildings, and so on? First of all, we need to highlight an increase of load due to the electrification. Electrification is an unstoppable trend right now, not only due to the electric mobility, but other technologies such as heat pumps, some other air conditioning equipment, or whatever other climate control technology, or so on. Okay, so due to electrification, we are going to have for sure an increase of, in the load of the distributed system. Then also we're going to have an increase of the distributed resource, mainly solar, but also other technologies like micro wind, micro turbines, and also other distributed resources not related with renewable energies. Okay, so finally, if we integrate all of these resources in a coordinated manner, we will create a grid congestion for sure. Let me illustrate this with a short example. Okay, this is a case of a study of a self-consumption scenario according to a specific Spanish regulation that it is very simple because it doesn't require paperwork from the point of view of the users, but it is forbidden to put the energy surplus into the neighborhood. So here we made this study for this presentation in the IEEE low voltage test feeder, but this is done for a real infrastructure. Okay, for confidentiality issues, we're going to show it with this IEEE standard, but later I will show you some examples using real systems. Okay, so here, for instance, we have in the left a specific house during the summer. In the right, the same house during the winter. Okay, and we assume that all houses here in this small system have electric vehicle. The electric vehicle charging is made during the night. For instance, we can see the electric vehicle charging here and the electric vehicle charging here. And also we have this PV panel generation during summer and PV panel generation during the winter. In the summer, we see that this orange curve represents the energy surplus. I can use this energy surplus for some thermal load, air conditioning, heat pumps, or whatever. And here we can see the state of charge of the battery. Okay, at 2 p.m. in the summer, the battery is fully charged, and I have energy surplus that I might use in another load. So this battery is 10 kilowatts hour. So why I shouldn't install a larger battery? Because during the summer we have less generation, less production of PV energy, so the battery is not full at any time of the day. Okay, so if I size the battery to be used correctly during the summer, then I'm wasting a lot of resources during the winter. But this is not what it is important thing. What it is important is that we test different penetration levels of PV production and also energy storage, and this is the effect that we obtain in the power transformer that is placed in the first node of the grid. Okay, for instance, with 0% of penetration of distributed generation, we can see that due to the electric vehicles, we have a huge peak during the night in the summer. Okay, but if we increase the penetration of distributed generation, this peak during the summer is reduced. Okay, and during the day hours, nearly I practically fit all the consumption with the distributed generation. Okay, this is during the summer, but if I go to a heavy cloud winter day, I see that the effect during the day of the penetration level is very low, even with 100%, and even with 100% of penetration, the peak consumption during the winter, it's extremely high. Okay, the effect over the peak consumption of the distributed generation is neglectable. Okay, so finally I have to size the power transformer for this peak. Okay, so even if I have this distributed generation, I need to make a huge investment in infrastructure. Okay, if I want to avoid this congestion. So with this, it is demonstrated that even adding a generation at distribution level, I will have problems of congestion in the distribution grid. How can I face this problem? Well, one possibility is make new investments. New investments in what? Basically, increasing the power, or the rated power of the power transformers and the net stations, and increasing the sections of the conductor. Okay, I don't know how the distribution business works in countries like Pakistan, India, Bangladesh, but I can tell you how it works in Europe. Electrical distribution in Europe, it's a regulated activity, and it's regulated by the different governments of the European Commission, European Union countries. Okay, so basically the government established a tariff, so the users have to pay this fixed tariff to the distributed, and also the government pays to the distributors depending on the investments that the distributors make in the network. So the more as a distributor, the more I invest in the network, the more money I get from the government. So in the past, when you discuss with a utility, why are you installing this transformer if you can install a smaller one? No, I want to install the bigger one because I receive more money for the investment. Okay, but so this is a very huge barrier in order to develop these kind of technologies for integration, because always the utilities wanted to install more and more and a bigger transformer, more sections in the wires and so on. But right now the regulators are reducing the remuneration that they receive the distributors. So this is a huge driver for this kind of technologies. As an example here, I show you a directive of the European Commission. Okay, I don't know if you are familiar of how this is working. This is working in Europe, but usually the European Commission publishes a directive. Okay, and it is quite flexible in terms of when this directive is applied in the different countries, because the different countries have different realities. So maybe a directive is applied in one country as soon as it is published by European Commission, but it takes 2, 3, or 4 years in other countries with different casuistics. Okay, but finally, all of them, they are applied. And look what directive it states. We should ensure the removal of those incentives to distribution tariff that are in detrimental of the overall efficiency of the system, and that might be a hamper participation of demand response, balancing market, and ancillary services. Okay, so this way of paying the distributors is totally opposite to the philosophy of this directive. Okay, because if I install a huge power transformer just to cover one specific peak that I just have for a very specific kind of day during the winter, this is not efficient anymore. Okay, so due to this directive, due to this change in regulation, the European Commission is forcing the regulators to change their minds. Okay, so how can I manage a massive penetration of these redistributed resources in a coordinated way without increasing the investment in infrastructure? Just managing the flexibility of the system. Okay, it is the only way. It is true that I'm going to have a huge increase of electrical load due to the electrification, but these new electric loads, as the previous presenter mentioned, they're not like lights or TV that it's being disconnected during a cricket cricket match and so on. Okay, these new loads that are going to be installed in the system are quite flexible loads. So let's see, for instance, sorry, let me try to just a minute. Yeah,
yeah, okay,
has some problems with the pointer. Okay, so
okay.
let's evaluate these loads. For instance, we have electric vehicles. Okay, the situation in Spain is 63,000 electric vehicles. Less than half are electric cars. Okay. This is the power consumption, the average power consumption, the average daily travel of a Spanish driver. So basically, that means 6.75 kilowatts hour per day for charging a electric vehicle in an average Spanish home. Okay, that means 2.5 megawatts per year. Okay, and even considering 100,000 electric vehicles, this is 250 gigawatts hour per year. Okay, in the total system. This is nothing for the generation system. This is just 1% of the global energy consumption. So we are not going to have problems for generating this energy, but we need to consider that the average Spanish house is consuming 3.5 megawatts per year. So if I add 2.5, I increase the consumption due to the electric vehicles in a 70%. So probably I will not have problems for generating that. but probably I will have problems for distributing that energy in the terminal distribution network. Okay, same thing for heat pumps, for instance. Heat pumps are nobody is speaking about heat pumps, but countries like Sweden, for instance, with nearly 2 million of devices installed, Italy nearly 2 million also, in Spain, and even when we are a very hot country, we have more than 500,000 of heat pumps. In 2018, we sold in Europe more than 1.3 million of devices. Okay, so I'm not going to go through all these numbers, but finally, for climate control in an average Spanish house, I need to spend around 1.9 megawatts. Okay, 9.1 megawatts, it's nothing, even considering more than 500,000 of devices installed. This is like 1,100 gigawatts hour a year. It's less than 0.5% of the total energy consumed in the country. But again, we are not going to have a problem for generating that, but probably we are going to have a problem for distributing that energy, because this is an increase of 54% of the average Spanish home consumption. Okay. Other agent, PV generation. Okay, nobody discuss right now about PV generation and the trend that is totally increasing in all parts of the world. Okay, but how this PV generation is integrated in the system, that depends a lot on the different countries. For instance, in countries like Romania, in the European Union, all the PV generation is made at utility scale. Okay, many plants are huge power plants with power transformer connected to the medium voltage system and so on. But in countries like Slovakia, 100% of the PV power installed are at a residential or commercial level. Okay, so they are integrated in the terminal distribution network. In Spain, the situation right now is that we have around 20% in the residential or commercial level, but these data are data published before the self-consumption royal decree that we have here in Spain. The expectations is that with this new self-consumption regulation, this percentage of 20% increase a lot, above 50% in a few years. Okay, so we will have a lot of PV generation installed in the system. But energy storage is a critical agent in this transformation. We see how the energy storage capacity from 2015 and the expectation for 2030, this increment is nearly exponential. Okay, and we can see here a very interesting data showing the cost of the kilowatt hour stored in a energy storage device. In 2015, it was estimated that each kilowatt hour that I store and I recover from an energy storage device, it has a cost of $0.25. Okay, these amounts are in American dollars. And if you see, the capacity installed in 2015 was around 40,000 megawatts hour. Okay, with 40,000 megawatts hour of installed capacity, I can cover less than 1 minute of world electricity demand. Okay, but see the forecasting. Okay, the forecasting for 2036 is that the cost of each kilowatt hour installed in a energy storage device is between 2 and 4 cents of dollar, and I will have installed 14 millions of megawatts hour. I can cover during 14 hours the total electricity demand in the whole world. Okay, so energy storage will be a key factor in the transformation of the distribution grid. So Well, this is a little bit the scenario. What the researchers have done over the last 20 years, we made a lot of efforts. Okay, we started 20 years ago with the definition of a microgrid as a solution for coordinating different distributed resources in a portion of network connected to the grid through a single point of coupling. But then the concept of a smart grid relaxed a little bit these topological restrictions, and we start talking about demand response and flexibility and so on. We have a lot of pilots testing this technology, but this is not something extended completely in a massive way in the network. Right now, we're talking about transactive energy. Transactive energy combines economic techniques with conventional network management in order to make a new, more intelligent and more efficient coordination of the resources in the network. Like we hear about peer-to-peer energy trading and this kind of new trends. Okay. I think that the aggregators will play a very important role in this transformation of the distribution grids. Okay. And when we talk about aggregators, we have different models. Okay. There is a vast catalog of aggregation models, and that depends in many factors like regulation, the available technology, the mind of the people and the population. And let's present here two very opposite models. The first one, the most simple one, an aggregator that, for instance, participate in the market, selling or buying this flexibility, or injecting or consuming more or less power depending on the price of the energy. We can see many examples of this, for instance, in UK. As an example, there is an aggregator that controls thousands of heating systems of water. So it coordinates when this heating system in the houses consume energy or when they do not. Okay, so depending on this coordination, he can increase or decrease the total power. But these houses, they are spread in the whole territory, okay, of UK. They are not concentrated in a geographical zone. So yes, as a business model, is it working? But is it solving any problem at distribution level? Is it solving any congestion problem in the distribution grid? No. Because also the price signal that it's receiving, it's coming from the pool of the transmission system operation. Okay, so the transmission system operation can reduce the price because there is a lot of energy surplus in wind or solar, but this price reduction will make this aggregator to consume more power, and probably in a specific zone of the distribution network, I have a congestion. Okay, so I'm not helping the distribution network. I'm doing the opposite. Okay, so as a business model, this aggregation model is working, and it's working fine, but it doesn't solve any problem in the grid. Which is the aggregation model that solves a problem? One in which a transmission system operator, distribution system operator, and aggregator works in a coordinated way. And the aggregator can provide to price signals and provide some kind of control to the loads in order to solve real congestion problem in the distribution system. Okay. However, this model, it's extremely difficult to implement for some reasons. Okay. One is that sometimes the activities, distribution, retail, commercialization, and these activities are separated and they are operated by different companies. So it is very difficult to coordinate all of them. And another important barrier is the situation in the utilities. Which is the reality in the utilities? Okay, the truth is that they made a tremendous effort during the last years to run the digitalizations of their assets. Okay, they created an immense volume of data. And the value of this data is, I mean, huge. But we need to remember one thing. They say that data is the oil of the 21st century. But I mean, I will say it in another way. Knowledge extracted from data is the oil. Okay, just the collection and storage of the data, does not mean that we are generating knowledge from this data. And the truth is that right now at a utility level, we have the data separated in many non-intercommunicated systems, and it's difficult to manipulate the data, make cross queries, and extract knowledge from it. Okay, for instance, right now we have the data from the smart meter coming to a database, then the geographical information system is feeding another database, the SCADA systems are feeding another database, and the inventory system is feeding another database, okay? This is not optimum at all, okay? So which is the path that we must follow? We need to use data lakes, put all the data in the same data lakes, and we need to implement systems that allow us to make a very fast and very complex queries, crossing a lot of sources of that data in a very fast way, okay? So this is the only way that we can make real-time interactions and fast analytics, intelligent reporting, and future projections in the system. And this is the only way in which we can integrate those smart buildings with a lot of distributed resources in the buildings. Again, this is difficult to do because sometimes this data belong to different actors or different companies. That's why in Spain, for instance, at ministry level, they are defining this common information model data in order to have a standard data model to exchange data between the different actors at distribution level. Okay, here is an example of a system. Let me make a little bit propaganda here. This is a paper that we published last year, a non-synthetic European low voltage test system. In this paper, we publish not only the geographical information data of this small system, but also the data coming from the smart meters and all the functions needed to create the mathematical model and run power flow. Okay, so if anyone of the attendants wants to make any kind of a study with an European low voltage test system, here we provide one with more than 10,000 nodes and more than 8,000 end user, and we provide our specific data model. Okay, here you can see the structure of the system. Power transformers are feeding through different lines to the buildings, but at least in Europe, we have a lot of possibilities for connecting in the low voltage system the two different power transformers. So we can create kind of meshes in low voltage and so on. Usually these systems are operated in a radial way. Even when I can create meshes, I always open one of the breakers, so I cannot create I operate the system in a radial way. Okay, so this is the real system, and this is the data model that we proposed. Okay, we need a data model very flexible, very robust, and very fast to operate, so we can make queries about all the elements in the system in a very fast way. And it is very important to remark that when we are talking about distribution systems, we cannot just translate the solution of the transmission level, because, for instance, the transmission network at Spanish level, 400 kilovolts, it has a few hundreds of nodes, okay? While the distribution system, just for a small town, has more than 10,000 nodes, okay? My region in Spain, it's called Asturias. We have around 1 million of inhabitants, and the distribution grid has more than 2.5 million nodes. Okay, so solutions that are working at transmission level, they are not working at a distribution level. So one key factor is the parallelization. We should be able to parallelize the computation in the distribution network, so we can do it in the time required for running applications in real time. Okay. Let me show you some examples of these complex queries that we make in different systems. This is, for instance, an impedance map. I think that it is better represented in this slide. We can see in every single point of the network the impedance from this point to the power transformer that fits this specific point. Okay, this is changing in real time according to the position of the breakers. Okay, and this is an example of a query that goes to the inventory of the breakers to check which is the position, but also goes to the topology of the network. Okay, so another example of complex query: voltage maps, running power flows, or currents map resulting from power flows in real time in the network. Okay, so if I really want to make a real-time operation of the terminal low voltage system, I need to run a state estimation, a real-time state estimation. Now, is it possible to do that? I mean, again, the key is the data management and the parallelization. And in Spain, let me talk a little bit about the system that we have for getting the data from the smart meters. We are using PLC technology, power line communication technology. This is a technology in which the smart meters injects the data into the electric wire, okay? And then I filter this high frequency signal at power transformer level, so I get the data from the smart meter, okay? So this data this technology, it's very good from some aspects. I'm not depending on a telecommunication company. The utility itself can manage the communication system, okay? And also another important thing is that I can extract data from the topology, the position of the breakers, and so on, just evaluating the paths or followed by the data injected by the smart meters, okay? But the bandwidth is quite low, okay? So even when the algorithms are already developed, the sampling process with this kind of technology is quite difficult, because from the PLC concentrator, I need to check one by one all the smart meters. So I need to ask, okay, smart meter 1, tell me the active power. The smart meter 1 replies. Smart meter 2, give me the active power, replies. 3 replies. Okay, so I need to make a sequential sampling. Okay, and this is, for example, one instance. One specific smart meter was requested to provide the active power at this time, okay? The answer was received at this time, okay? Nearly 40 seconds later. So finally, I received the information with a timestamp that it's a time between the request time and the answer time, okay? But finally, the delay is 34 seconds, okay? This delay depends on the injection phase, the distance of the concentrator, the saturation of the network, the electromagnetic interferences, and many other factors, okay? So look, for instance, this is an example of a sampling of 30 dwellings divided into 5 different buildings, okay? And these are the distance. So the slowest smart meter took nearly 20 seconds to reply, and the fastest an average of 7.81 seconds, okay? So finally, the number of records obtained during a whole day of each smart meter is 181, okay? As an average, I obtained a record of all smart meters of the grid each nearly 8 minutes. So is it possible to run a state estimation with this data? Look, this is in black, you have the real signal, and in red, you have the sampled signal by the smart meters, okay? So you can see that it's quite similar, but in some cases, like for instance here, this is the data that is coming from the smart meter because I have a delay in the sampling, and this is the real data, okay? And the opposite. So is it real to run a state estimation using this kind of technology for communication? Yes, but I mean, you need to use a lot of artificial intelligence and a lot of forecasting. You need to optimize how the sampling of the measurements is done, and so on. And finally, for just to finalize my presentation, all of these things that we are doing, I mean, we are just in the second evolution of what it was called smart grid. You know that electrical engineers, we need to publish. So for publish, we need to be inventing new terms every day. Okay, so smart grid is already an old terminology. Okay, right now people are speaking about neural grid, and which is neural grid? Neural grid is just an evolution of the term of smart grid. Is the possibility of dealing with the huge amount of information that we are generating at distribution level and being able to use this information to make a real-time operation of this distribution level. And this is the only way that we have for integrating these smart buildings with a lot of distributed resource and a lot of flexible networks. Okay, all of these technologies, smart buildings, flexible loads, electric vehicles, whatever, if they are not coordinated in an appropriate way, then they are useless. Okay, so technologies, enabling technologies for what we call the neural grid. Well, the previous dimensions, of course, but then connectivity, fiber, low power wide area communications, 4G, 5G, they will be present into the network. Low cost sensors also combined with advanced measurement infrastructure. Right now, the smart meters, they are very accurate and they are quite expensive, but we can combine these smart meters that are very expensive with very cheap sensors that measure not only electrical consumptions, but also temperature and also other factors. Okay, cloud and edge computing, it is important. Okay, we are not going to just get all the information and process this information in a central computer. A cloud computer is going to be very important, but also edge computer at different levels will be also very important. Of course, artificial intelligence, which will be the brain of this future neural grid. Of course, artificial intelligence, cybersecurity, it will be a critical point. Okay, because if we create a system that can be operated remotely with a lot of data sharing, a lot of artificial intelligence, then we need to protect that system against cyber attacks, because it's going to be very vulnerable. Okay, and finally, drones and robotics, that will be the basics for advanced monitoring, maintenance, and repair activities. So this is not a revolution in the grid, but just an evolution. As I told you, we start 20 years ago talking about microgrids, and then we moved to smart grids, demand response, transactive energy, and in a few years we will have, of course, implemented what we call this neural grid. And this is everything from my side. Thank you very much for this invitation. And right now I'm available for any question that you have.
Thank you, Professor Pablo, for an excellent presentation. It was really data intensive. So I think the audience must have really got a lot of new information from that. We shall now take a few questions that we have received. So the first question is from Bhutan, is what type of conductors are used for distribution systems in Europe, if you have any comment on that?
I mean, typically in distribution, you know that at transmission level we use a lot aluminum conductors. At distribution level, typical conductors are made of copper. Okay, copper conductors, three-phase lines with 4 wires. What is important to mention is that I don't know there, but in Europe, the grounding system it is the typical labeled as TT. Okay, that means that the neutral conductor is grounded at power transformer level. Each line fed by the power transformer level has 3 wires plus the neutral that is grounded at a power transformer level, but then it is not grounded anymore. So imbalances can create important neutral voltages in Europe, and this is something that we must also control.
Okay, thank you. The next question is from New Jersey. How the instabilities injected by variable renewable energy resources like solar into the grid mitigated? He's asking because the higher the penetration levels, the greater the instabilities in the grid.
Well, I mean, we could make a curtailment always, okay? Just be able to reduce the energy injected by the PV panels. But this is, from my point of view, this is not a very smart way of dealing with the PV panels. The only way of dealing with this is kind of stochastic and intermittent loads, from my point of view, is real-time operation, the capacity of operate that in real time, and the capacity of sending commands to the energy storage devices in order to somehow control the total effect of this. Well, it is many people talk about the stochastic nature of the renewable energy. Right now, with the forecasting techniques, it's not so stochastic. I mean, the amount of PV energy that I can install in a specific location with a specific infrastructure, I mean, we can predict it in the short time. Okay, so it's not very stochastic, but yes, my answer is definitely controlling in real time the energy storage system, so we can make some kind of a balance and mitigate all problems of over injection or and so on. Okay.
Given that grids have limited hosting capacity for distributed generators, how is achieving 100% penetration possible?
100% penetration, it is only possible with two words: real-time operation and energy storage. Combining that, it is possible to reach that 100% penetration. If not, the only alternative is infrastructure investment. Okay, biggest power transformer, biggest section in the wires, and so on. So we have two alternatives: the conventional hardware alternative of making a lot of investments and deal with the grid in a very inefficient way, and then what we call software alternative, be able to manage in real time the resources, so we can reach this level of penetration without increasing the investments.
Okay, the next question is, for real-time estimation, phasor measurement unit is also an option for the collection of data. What do you say about that? By using machine learning with PMU, is it beneficial?
Well, for sure. I mean, for running a real-time state estimation, we need to, right now in Europe, we have this technology, PLC, okay, that limits somehow the sampling frequency. So this drawback must be overcome for sure with machine learning and this kind of techniques. I'm going to give you an example of that. For a specific house, if we need to request for the active power and then wait for the active power data to be received and then make a request for receiving the reactive power, then I spend twice the time of that I spend in requesting one data. But it is possible to create kind of a machine learning application. So depending on the active power level, I automatically estimate the reactive power. So I do not need to make two requests. I just make one request. Okay. So of course, optimal sampling combined with artificial intelligence is the way that we should go. Okay.
Perfect. Thank you. The next question is, should regulator enforce buildings to follow energy storage or renewable sources, or is it financially viable for the building's residential consumers?
Well, right now, at a European level, the regulator is not forcing to a specific technology, like, for instance, PV or energy storage and so on. But there is a directive stating that by this year, all public buildings should be nearly zero energy buildings. And that means that from the point of view of electrical and thermal, okay? So this directive is not being fulfilled right now in all the countries at the same time. But I mean, as I told you before, when there is a European directive, some countries adopt this directive very soon, and other countries, they are quite flexible. But finally, everyone must adopt it. So right now, all public buildings should be nearly zero energy buildings, and this is just a starting point. Okay.
Okay. The next question we have is how many, what's the percentage consumers big data analysis being done by Spanish utilities? Is there a separate service provider for big data analysis?
Well, I don't get the question very much. Usually the problem with the data owned by the utilities is that this confidentiality problem. Okay, so there is no way that utilities put in common this data, and some third party specialized in big data use this data for making data analysis. So each utility makes its own big data analysis and management of the data.
Okay, thank you. The next question is we have the penetration of renewable. I think this is the follow-up question to the penetration of renewable energy sources. So the penetration of renewable energy resources is solved only when we use the demand side management concept, which is basically smart grid. Please give your reviews on that.
I mean, I can tell you data at the Spanish level. Okay, at the Spanish level, the installed power in renewable energy is around 30% of the total power. Okay, so we have a huge amount of renewable installed in the grid. Wind turbines, and mostly also PV, hydro, renewable energy. However, most of this renewable energy is installed in huge power plants. Okay, huge wind parks, huge PV plants, and so on. The penetration of renewable energy at terminal distribution level is still neglectable. Okay, we think that with this new royal decree about self-consumption regulation, it's going to increase a lot during the next years. But right now, at low voltage distribution system, it's very few penetration. Okay.
Okay, thank you. Next question is from Pakistan. What would be acting as backup in case of cyber attacks on smart grid or neural grid systems?
Well, I mean, this is an issue that has been discussed a lot. Okay, we should have some kind of hybrid centralized distributed control. So somehow the distributed resources should be able to operate in a distributed way, even if they are not operating in a very efficient way. But without a central coordination, they should be able to do some functions. Okay, this is the only way of protecting the system against a massive cyber attack. Okay, so even if I just cut the communication with the central controller, all the distributed resources will be acting in an active way according to some rules. Okay, of course, this distributed operation will not be optimal, but what we want is that to be efficient during the instance in which the communication is interrupted.
Perfect. The next question is there any pilot project for real-time state estimation for 8-minute data from smart meters around the globe?
Well, we are running one. We are running one. I show you this data, and we are trying. Okay, we're trying to run this in with a utility that we have collaborations. But as I told you, it's really, really, really hard. Okay, it is really hard because right now the sampling frequency that we have from the smart meters is very low, and it's limited. I mean, there is nothing that we can do for incrementing this sampling frequency, but just changing the technology of the smart meters. And the thing is that this technology is a technology massively adopted in Europe. So we have tens of millions of devices installed with this technology. So right now we need to deal with that. Okay, we're not thinking about changing the technology because we cannot make a real-time state estimation.
Okay, the last question is, in SAARC countries, most of us don't have competitive market regime. Will the aggregator models that you presented will be applicable without it?
Sorry, I didn't. Can you?
I can repeat. Yeah.
Yes.
In SAARC countries, most of the countries don't have competitive market regime in the electrical sector. So the aggregator models that you presented in your presentation, will they be applicable without the competitive market?
Yes, I mean, the economic target is just one of the targets that aggregator may have, okay? But another target will be, for instance, an energy community in which the aggregator controls all the resources in order to reduce the amount of energy exchanges with the grid. Okay, so this is an example of how an aggregation model could be implemented in a non-competitive or non-market environment. Okay, that is not a problem at all.
Okay, so that's it from our side. I think we have answered all of the questions that we got. So thank you again for being a part of this webinar, and I hope that we can collaborate in future as well.
Thank you, Ahmad, for your invitation. It was my pleasure to talk to you, to keep contact, and to attend to this webinar. Okay.
Okay, excellent, excellent. So I'll be sharing the link with all the data that we have for this webinar. So thank you again, and take care, and goodbye. Dear audience, I'm sure that you must have benefited from today's enlightening discussion. Experts try to convey their insights on grid interaction of buildings and the flexibility that can be added to the grid through the coordinated installation of grid interactive buildings, electric vehicles, and other such consumer-owned resources. To conclude the discussion, it's worthwhile to mention that building to grid integration can result in numerous benefits, including in improving energy affordability, enhancing grid reliability, and reducing grid congestion. With increasing digitization of the grid and enabling communication technology, better utilization of available resources is possible, and the resource owner can economically benefit through transparent energy transactions. Given the potential of the SAARC region, the grid interactive consumer resources can play an important role in the sustainable development of our region. Dear audience, we now have come to the end of our webinar. I once again would like to thank our speakers for today for taking their time out of their busy schedules. And thank you all of you as well for joining us in today and sending us all of your questions. We apologize again if we couldn't answer your question, but you can also provide your feedback to by email to rftt@saarcenergy.org. And if you would like to follow up with any of our experts today for any relevant data or connections, we can help you with that as well. I would like to reiterate that all materials relevant to this webinar will be available on SEC website, which is www.saarcenergy.org. So that's it from our side. Take care, stay home, stay safe, and goodbye.